in a camera too.
I don't have the software to operate it.
But let me see if I can.
Yeah, no, sure.
Because we did it here, but what the heck it was? No, it's not that one. Suraj knows how to do it, but we don't. So we just keep it. We just gonna make it in a way that.
We should move the camera then,
Okay.
right?
I guess so.
Is it okay?
The other, I think I want my face more here, right?
Yeah, and you can move.
No. No, but now we lost the screen, yeah?
But you can move this whole thing. How you like this?
Yeah, okay.
Oh, now this is very good. Now when you're standing, I think it is perfect. I think it is perfect.
Really?
Yes, I think so.
Okay, yeah, let me...
Like this, when you're standing, when you're gonna stand there, it's gonna look.
Oh,
very
you
good.
want to stand or do you want me sitting?
If you stand, it's gonna be perfect. Let's try. So if you're gonna be there,
Yes.
bit more that direction. Still more like that direction. I think it is getting really, really good. Only thing is that I don't know how to crop this one here away. Hey guys, again, we're gonna do the settings, and as soon as we're done, we're gonna go. I need to call Suraj and ask help to get started, and then we will go. Hey Suraj, how are you cropping this camera in OBS? Okay. Alt. Okay, Alt, and then
Alt?
and then like that.
No.
No.
I don't know what Alt is. Yeah!
There it is. There it is. A
Oh.
bit more that direction.
Yeah.
So we found it. So we could. No, it's okay. It's okay.
We've done.
Yeah, it's very good. It's okay.
I learned something. Thank you.
Okay, so we're good to go. Thanks.
Just like this. Yeah, okay. And now, let me see.
And you see how it is here.
Yeah,
It comes with this low latency though. So
of course.
look, very good. So it's looking very, very good.
job. Yeah.
And then mic check.
Yes.
Oh, yeah.
Oh my God, it's so good.
Yeah, but it's because
Also,
of you.
is it okay?
You're the OBS
don't you want to try this presentation mode? Because we
God
want to
damn
see
it! So
whether
we need
it's...
to put still this on.
Yeah.
This is the one thing that is missing. So do you have anything to connect this with?
Yeah, I have.
Oh, I don't want to use any power than that. Any more power than that.
That doesn't matter. No, that's okay. That's okay. It's okay.
We're getting close. We're almost there. The final thing missing is that you guys don't see anything yet. The one thing that I did. Okay. What's this? Sorry about that. So you're missing the view. What number is this? This HDMI one.
1. Oh, no.
But look how good is the streaming. It is really good.
Less than 5 seconds.
Less than 5 seconds latency. That's good too. Look at us. So we're getting better. So we're getting much better all the time. Every week we're improving a bit.
Okay, for this kind of,
Yeah, it's okay.
No, that's okay because
It's okay.
it's about...
This guy is slow. What is this? Still no. I think that there's something wrong in this projector or something wrong in that switch. It's just not willing to show how it look. You know, it's all the time empty. So let me do this, because a week ago we were have to do this. So we were using. Still nothing. No, it's this one.
Oh, yeah.
Okay, so I can do this.
And then put that. Yes, exactly.
Okay, what do you think about the lighting conditions? Should that be
Up. This should be more up. For
Which
the
one?
Green screen.
so? Which should be more up?
For the green screen, I need more lights here.
Okay, where we can get that one? Here. Screen is still not perfect, so it's okay. So maybe one thing we can do is that we can make you a bit smaller. But no, that's okay.
No, it's okay. It's okay.
That's okay.
It's okay.
What do you guys say? It's okay. I think
Well,
it is
there's one
okay.
problem we have to solve.
Oh, what's that?
If I now point like this,
Is what?
the audience sees my green thing, but the stream sees nothing.
On the stream.
But we
Yeah,
cannot
that's
solve
that's
that.
the price you have to pay if you want to participate online.
Exactly.
So it comes with the consequences.
Okay,
So
that
it's
was
no
a-
way. It's always not the free of charge. But what about Musta? But what about these lights? Because there's one more row of lights. Should we try to put it on? Ah.
That's even. Well, yeah,
All
let's
right.
wait.
So,
That should
all
be
right, guys.
better.
Finally getting started. And again, late, but not much anymore because it's 7 minutes only. A week ago it was, I think, at what was it, 15 minutes or not 50. It was a 1-5.
We are a great team, Aki.
It
We
was
are
less than
great.
a 50, I think. I hope that it was less than a 50. But you know how it is. So all these courses getting started in a chaotic way. We need to take some time to learn these settings. If we would stay all the time in the same lecture, it would be so easy.
It's
So
going
easy.
to be 1 hour and a half. Like no.
I don't know. Ask Aki. I have no clue.
So we're gonna be here roughly an hour.
An hour.
Oh, an hour. Yeah,
An hour.
an hour. Yes.
So until 1:15.
Oh,
Yes.
okay.
So we got okay. So as promised, so this course we have a lot of visitors, and the first visitor, which is getting started really from the outstanding way, is Professor Arjen Swart from Delft University of Technology. Arjen is my good friend, and we've been knowing each other a little more than 100 years, and I think correct me if I'm wrong, but I think we met when there was this big incident in U.S. September 11, 2001.
Exactly.
There was a conference in Pittsburgh at that time, and I was a postdoc in Chicago, and we met in this conference. And when this attack happened, they evacuated the entire downtown of Pittsburgh, except our conference, because there's a bigger thing than terrorist attack. And the bigger thing that the terrorist attack is a multibody system dynamics.
Exactly.
And, and the conference related to that. So we met there, and traveling back to Europe, me back to Chicago was very, very difficult because they canceled all the flights for several days.
Yes.
And then finally I was able to find my way back to Chicago, and you find your way back to
Via Ithaca, Cornell.
Okay, so it was
all
a
kind of
lot of
cars
detouring,
and-
but finally you made it.
Made it.
And I made it, and what was a consequence of this was that we get to know each other, and we've been friends ever since.
Yeah.
Now, that was roughly the time you started your sabbatical.
Exactly.
Okay, so you went to
University.
Cornell University, and you started to learn new things about bicycle. New thing about bicycle. So how new is this bicycle business? So it's recently discovered, I think, a couple of years back, and it's quite amazing that you can still take a look at the bicycle. And that's when you started this bicycle dynamics, and you even established the bicycle dynamics lab. And a few years after, you published a paper in Science related to bicycle dynamics. So here's our first guy, at least first that I know from the field of mechanical engineering, publishing in Science. So it's possible. It is possible. You just need to dream big. And what was the paper about? And what's the whole thing about the bicycle dynamics? That's what you're going to learn next.
Exactly.
And as promised, Arjen is willing to answer questions that are related to vehicles in general.
Yeah.
Railroad, that's okay if you want to learn that. If you want to learn what else?
Cars.
Cars, it's okay too.
Thank you, Aki, for the very nice introduction. And it's my pleasure to give a presentation here in this course of as I said, Aki said, I'm from Delft University of Technology in the Netherlands. And I'm going to talk now about bicycle dynamics and control. I'm not a vehicle dynamics specialist. I'm in theoretical and applied mechanics. But, well, you need applications, right? And one of the applications is the bicycle, because there's a lot of dynamics going on in a bike. So the motto of my presentation, that's interesting, the latency, but okay, forget it. So the motto of my presentation is everyone knows how a bicycle is constructed, right? It's two wheels and a steering assembly. Nothing more, nothing less. Pretty simple. Yet nobody fully understands its operation. And with the nobody, I include myself. Although I'm running the bike lab now already for 22 years or something like that. And yes, I'm in bicycle dynamics and control, but I still have a hard time understanding some of these things. So that is the motto.
But don't worry, these guys comes with a big brain, so they can understand concepts, very, very difficult
course.
concepts with no problem whatsoever. So if you ask like any doubts, any questions,
They have the answer. Thank you, Aki. Well, first of all, I could not have done this work by myself. To get somewhere in science, you always have to work together, to have to collaborate. Of course, I had a lot of collaborators at TU Delft. Then at Cornell University, where I had my sabbatical, as Aki explained in the introduction. Andy Ruina was my host, and Jim Papadopoulos, who was actually the real bike genius, and then a number of students there. And UC Davis, Mont Hubbard, and Jason Moore. Jason Moore is actually my successor in the bike lab because you see at the color of my hair, I'm actually now already an emeritus professor. Yeah. But of course, like with professors, you just keep on working, right? What else can you do? Okay, let's start with some observations in this bicycle dynamics. And for the observations, I want to show you a part from a movie. The movie is called Jour de Fête by Jacques Tati, and it's from 1949, and it's about a postman who wants to rationalize things. And he rationalized things by using a bicycle. Instead of walking, he now uses a bike. Really American way, everything fast. You see a bike moving by itself, and everybody said, well, that's of course a trick, right? Because in movies, everything is a trick, so a bike cannot move by itself. That is impossible. It will just fall down. However, this is not a trick. If you take some random bike and you go to a car park, you give it some speed, you release it, it will stay upright. And we usually call this then a stable configuration, stable steady motion. You can say this is stable, but I would say it's super stable because you can not only push it forward, but you can always give it some initial speed and then hit it sideways. So we propel it, we hit it sideways, it starts oscillating, and then the oscillation dies out. And that means that it's super stable. Now, of course, you would think, where does that come from? We as mechanical engineers, we think of systems with dying oscillations, that there is like damping in the system. Well, if you now look at the bike, how much damping in a mechanical sense is there going on? There may be some friction in the tires with the road, some scrubbing. There may be some friction in the joints, maybe some air drag. But at these low speeds and so on, nothing much is going on. I mean, given some initial speed, you can pretty nicely coast for a while without really slowing down. So where does this stability come from? Well, of course, the bicycle is already very old, right? It's even older than we are. Can you imagine? So it started around 1849 with a hobby horse by Karl von Drais, and then there was an evolution in the system. And the evolution had to do with a gene which we have in our body. And everybody has this gene. And this gene in your body tells you one thing all the time: faster, faster. So whatever you do, the gene says faster. With every action, always has to go faster. And especially also in bicycles. So propelling with your feet on the ground, you don't go so fast. So what do? You invent pedals on the front wheel. Now you can go faster. Still, that's not enough. So what do? Well, you can pedal faster, or you can make the wheel bigger. Then you don't have to pedal faster, but you go faster, right? Until there's a certain limit, and it has to do with sizes in your body and so on. I mean, how big can the wheel get? And now you see very nicely a jump in evolution. Instead of the front wheel propelling, we do a chain drive to the rear wheel. But it's evolution because we still have this large front wheel. And then somebody says, well, actually we don't need that, right? And he makes one with a very small front wheel, just to demonstrate the point. Then we continue, and then we are here in 1899 or 1890, around that time. And that is the bike as we see it today. 2 equal-sized wheels, a chain drive, and pneumatic tires. And if you look outside, your bike looks like this. Nothing much different. Maybe the color, or maybe some electric thing going on with some people. But anyway, this is the basic design, right? Now, around that time, in that 1890s, of course, scientists also noticed this behavior, this stability. Like at 0 speed, it falls over. Given some forward speed, it stays upright. And scientists would like to explain things, so what we do, we make models, and with those models, we examine what's going on. Both in the UK, Whipple, as in France, Carvalho, studied the same problem, and they made a model, a simplified model, where we have a lot of assumptions. That's what we do in engineering. When we look at the system, we say, that's very complex. Let's assume it's a rigid body. That's the first thing we do. So we assume that the rigid bodies, wheels and the riders and so on, we fix even the rider on the bike. He cannot move with respect to the bike. No operation of the handlebars, just hands-free. Everything symmetric, knife-edged wheels, point contact, no side slip, flat level road, no friction propulsion. A lot of assumptions to come down to a simplified mechanical system which has 3 velocity degrees of freedom. Meaning, the bike can move back and forth, it can lean left and right, and you can steer. So those are the 3 degrees of freedom, right? Note, by the way, if you look at all these assumptions, that the system is energy conservative. And that conflicts a little bit with the thing we saw before. We saw a dying oscillation. So, I mean, how can you imagine as an engineer a dying oscillation and there's no energy loss? Like, there seems to be a conflict there. So what's going on? Well, what do we do as engineers? If we want to study the dynamics of a mechanical system, we write down the equations of motion, right? And from that equation of motion, we can simulate the motion with some multibody dynamic software or whatever. We derive the equations by hand. But in this case, we are not interested in the motion, but we are interested in the stability of the motion. Meaning, we take the equations of motion, we linearize them about a configuration, and the configuration in this case is the upright configuration, where the bike moves at a constant forward speed. And then we say, well, small changes with respect to that steady motion. So small changes in speed, small changes in the lateral motions. And the lateral motions are then the roll angle, the steer angle, and the forward speed. That's the forward motion. Now, for an upright bicycle, the lateral motion, so the roll of the frame and the steering angle, so the roll of the rear frame and the steering angle, are these lateral motions are decoupled from the forward motion to the first order. So we end up with one very simple differential equation, V dot is 0 or V is constant as a solution. And the other one is just two second order differential equations coupled between the roll and the steer. And it looks maybe complicated because we wrote it in a little bit of form where we pull out terms which we understand. But in essence, it's mass times acceleration equals forces. So these are just forces. But these are forces where we linearize them with respect to lateral motion. So these are stiffnesses. So this is gravitational stiffness. This is a stiffness contribution which is proportional to the square of the speed, and it has to do with curvature. If you go about curves, you get these, well, you could say centrifugal or centripetal forces. So that is an effect. And then we have here also forces which are linear in the forward speed and in the time derivative of degrees of freedom. And you could say that reads like sort of a damping type of thing. But of course there's no real damping going on. Maybe it's a gyroscopic thing because of the rotating wheels. Now if we look at this C thing, it has on the diagonal a number, a positive number, so that it seems like damping. It's not skew symmetric, otherwise it would be not energy conservative, but it's not. And actually we at this stage we don't understand what that is. But it doesn't matter. These are linearized equations of motion. We use them to then investigate the motion. So small motions for the lateral behavior, the roll and the steer. We assume exponential motions, put that in the equation, get a characteristic equation, which is to the fourth order, two second order differential equations. And of course, then we can solve that characteristic equation. And since speed, forward speed, is of interest for us because we saw the stability heavily depends on the forward speed. I mean, maybe also on the wheelbase or the head angle or whatever, but forward speed is now a very interesting parameter. So we plot.
Just a comment to audience. So this is still multibody. This is a little bit of special multibody, but this multibody.
It is multibody because we have one wheel, we have a frame, we have a front wheel, and we have a steering assembly. So those are the four bodies connected.
It's just that in this class we haven't really discussed about this kind of the constraint you use here, which is rolling without slipping.
Exactly.
But that's just another kind of the constraint.
It lives in a different world. But it's a constraint.
Concept-wise, we're not so far off from what you know.
Exactly.
And then this linearization is something we haven't discussed much, but you can do it too.
Yeah. Okay, so we calculate the eigenvalues. So we assume exponential motions. We calculate the eigenvalues of the system, like in a pendulum. You have this eigenvalues of square root over L over G, and it tells you about the oscillation of the pendulum, or about the instability, if it's plus or minus. Anyway, the eigenvalues for four pieces. Then at zero speed, you have A, B, and minus AB, because there's these symmetries going on at zero speed. But then when speed increases, eigenvalues, the real part is blue, they come together and they form a conjugated pair. And a conjugated pair means this is imaginary number, meaning oscillations can occur. Exponential to an exponential function to the power of an imaginary thing is a cosine sine. It's an oscillating thing. So we get an oscillating solution. However, the real part is still positive, so the oscillation is unstable. When speed then increases, it becomes negative, the real part, and the thing is stable. The other roots are also interesting. They also have to do with motion. So this was this oscillating motions which we saw. Then the other roots are, this is what we call caster mode, meaning that the front wheel, if there's a small change from the steering, it will quickly come back to you, like in a shopping cart or a desk chair where you have these caster wheels. And the other one is what we call capsize mode. It starts stable and becomes at high speed mildly unstable. And capsize mode is like in a ship that you slowly go over like this, that you follow. Not so interesting for now. The most interesting one is this oscillating one, oscillating unstable and becoming stable. So the bottom line is this very simple 3-degree of freedom model already predicts that the bike can be stabilized by going faster, right? That is nice to see. Stability depends on the velocity. Now what we do, this is real multibody, which now I'm going to show you. So this was just equations before that. On the right you see a real multibody simulation. A bike moving forward at slow speed starts to oscillate, and exactly this is what happens when you learn to ride a bike. You find it scary, you don't know how to operate it, you don't go so fast, so you will crash. The thing is very unstable. And you don't know actually how to balance that, as predicted also by the eigenvalues. Then the next step is, of course, that we increase the speed, that we come into the stable region. Again, we're going to do there the multi-body dynamic simulation. We propel the bike up to speed, we give it some lateral, some hit, and then you see the oscillation, and you see that oscillation dying out. So yes, the model, the linearized model predicts this stability. If we do, that's for small angles, etc. If we do really large angles, as in real life, still we see the same behavior. Well, the big question is now, of course, why does this system behave like it does? Where does this self-stability come from? And I always call this self-stability auto-magic control. Not automatic, but auto-magic. Because to me it's totally magic how a system like a bike can stabilize itself. I mean, if you take a stick like this, and it's in an unstable configuration, it falls over. And if you take a bike, you put it there, and you release it without any speed, bang, it falls over, right? So, given some speed, it stays upright. How does it stay upright? Actually, that's a very hard question. So let's make a bit simpler question, and let's say to ourselves, how do we balance a bike? Because at slow speed we have to balance a bike. If we understand how we do it, maybe the bike can do that by itself and we know what it is doing. And now comes a question for you. Who does not ride a bicycle? Okay, so everybody rides a bicycle, right? Then can you ride at slow speed? Yeah, no problem. So you can control a bicycle even when it's unstable. Okay. Can somebody tell me how he controls the bicycle? What are you doing to keep the thing upright? Yeah.
Maybe shift weights between your two legs and maybe the steering wheel to the side you're falling, you're trying to balance it.
Yeah. So you move your upper body and you start to steer, and
I think speed is really important to control the person.
but you have to go slow because the guy in front of you goes slow, so you cannot increase your speed.
Stable the center of gravity by stabilizing the center of gravity.
Yeah. And how do you do that?
By changing the position of my body,
Yeah.
so that it will be always stable. It will be always in the same position.
So you look for a static equilibrium. And the bike can do that. The bike is very smart, right? It has brains. Well, actually, if I ask myself, what am I doing to balance a bike? I don't know. I really don't know. I mean, I'm steering, yes, and I'm moving my upper body, but what am I exactly doing? What are the cues? And suppose I wait a little bit with that. Can I still balance them? And you can do the experiment by drinking alcohol or something like that, because then I automatically wait a lot. I don't do this at home, of course. You do everything a little bit slower. But actually, I have no idea. So let's go to a simpler problem, and that is, how do you balance a stick on your hand? Well, that's super simple, right? You have a stick, and yeah, I even can do it. So what am I doing? So I notice that the stick is falling over. It's falling over to the left. Then what do? I move the support underneath. And falling to the right, I move the support underneath. So by moving the support underneath the center of gravity, as you said, you can balance that stick. Okay, well, if we know how we balance a stick, then we move to the bicycle and say, okay, in the bike we can do the same. So what do? We move the contact points, yeah. So we move Earth, right? That's not, we cannot move contact points directly in a bike. However, if a bike is moving forward, you have a steering assembly. And if you rotate the steering assembly on a moving bike, your contact points will move laterally. So if you move forward and you steer to the left, your contact points will go to the left. Okay. So now you are falling to the left. So you have to move your contact points to the left, right? In which direction would you be steering? To the left. So now we have a very strange system. You fall to the left, and instead of saying, hey, I steer to the right because this is not going right, you have to steer to that same direction. So you fall to the left, and on a moving bike, if you steer to the left, you come upright again. That sounds strange? Yes.
Is there any relation between stability and width of tire?
And?
Is there any relation between stability and width of tire?
Tire?
Width.
The width.
So,
Yeah, the width of the tire.
Yeah.
No, well, you can make a model where the tire has a toroidal shape, like in motorcycles, and yes, then the contact moment moves a little bit laterally, and that helps you in stabilizing. But it's only a very small contribution. Whereas if you just turn the handlebars, they move very quickly. And they move with lateral acceleration, and that's about proportional to v squared divided by the wheelbase times the steer angle. So this is really a very strong mechanism, because this lateral acceleration is proportional to the steer angle. And of course your speed, if you go faster, it goes faster. Whereas this shifting is very small contribution. Yes, it works, but it's not sufficient. So the mechanism to balance a bike is fall to the left, steer to the left. Fall to the right, steer to the right. And that sounds very counterintuitive. And I like to invite you to do the experiment. And by doing the experiment, the best thing is that you just cycle, not holding the handlebars with your hands, but with your open hands, push like this. And if you then push with your right hand, you will notice, bang, the bike will immediately fall over, or with the other one. And you will notice what you are doing. So that is a nice experiment to do. To show that that really works, at Delft, students have to do projects, right? And one of the projects in the older days was with Lego Mindstorms. I don't know if it's still available nowadays, but Lego Mindstorms was Legos with motors and electronics. So this student, Joep, he built, instead of a walking robot, he built a motorcycle. So with Legos, with a steering motor, propulsion motor, with a sensor about sensing what is the state of the system, and a computer to control the steering motor and the propulsion motor to stabilize the machine. He thought, well, I'm in business now because from the motors I know the rotation angle and the speed, and I can change the speed of the rotation, and with the sensor I can sense how the rear frame is moving, and with the computer I can make a nice control algorithm and then balance the whole thing. Now Joep was a motorcycle rider and he was good at it, but he couldn't get the thing stabilized. So he had an idea about what he was doing on a motorbike to balance, but that idea didn't work in his machine, or his idea was maybe wrong, who knows. Code after line in the controller, nothing worked. He had to go for an internship, and he got into a sort of a panic state, and they said, well, there's a bike lab in the back there with Schwab, and maybe he can help you. I said, well, actually the problem is not so difficult. You have to you have to steer into the fall. So if you fall to the left, steer to the left. If you fall to the right, steer to the right. And you're an engineer, so what do you have at hand at the machine? Well, you have a steering motor, and that's probably a DC motor. So the amount of torque you apply is the amount of voltage you apply. So let's say the steer torque we apply should be proportional to the amount you're falling over. And how do you sense falling over? Well, you have probably some rate sensor from an IMU there, where you measure the angular rate. So you say motor voltage is proportional to angular rate, and it can be 10 times or minus 10 or 100 or minus 100. I don't know about the gains and the sign. You have to fiddle a little bit, but that should work. And then I was quiet. He looked me in the eye. I said, "You, what's going on? Get working." He said, "Is that a problem?" I said, "Well, yeah. It's one line of code in my controller." I said, "Yeah, okay." Oh, nothing to be said, so he went away. And then I think within 3 minutes, he came back and he showed me this video. We see a bicycle or a motorcycle being balanced while riding by means of steer into the fall. So this is the living proof that it works. Steering into the fall is the mechanism. And the same thing, as you saw here, you can see, of course, also in the bicycle experiment, which we did in the car park, right? We had it propelled. You see it leaning to the left, then it steers to the left. You see it leaning to the right, then steering to the right. So it steers into the undesired fall, and by such it can balance itself. Okay, so steering to the fall, that is the balancing mechanism. Still sounds a bit automagic, because why does it steer into the fall? What system does make it steer into the fall at the right time, the right amount? So you could, or in other words, a bicycle is self-stable because, why does it do it that? Well, there are actually two teams in that. Like in life, with the left and the right, or the screeches and the sneeches, or the red and the blue, or whatever. Here you also have two teams. One team says, oh, it's obvious. You see in a moving bike, these wheels, and they are rotating wheels, and then you have gyroscopic effect, of course, because it's a sort of a gyroscope, and it moves in a three-dimensional world, and it's rotating, and then it rotates about under axis, and then it sort of stabilizes itself, like in any gyroscope, you know. It's clear, right? Well, and that's the left, and then the right people say, no way. That's only a very small contribution, and maybe the sign is even wrong, and who knows? No. It's not gyroscope. It's because of this strange steering geometry which we have. Because the steering axis hits the ground here, and then the contact point is behind that where it hits the ground. So it's like a caster wheel, and that caster wheel follows you, and that is the whole mechanism. If you lean the bike, it starts steering also, and so clearly this is the mechanism. Yeah, what to do, eh? So what is now the answer? Well, of course, let's first look at the gyroscopic effect. That explanation is already very old. So in around 1910, there were two eminent scientists, Felix Klein, famous from the Klein bottle, and Arnold Sommerfeld, nominated 81 times for the Nobel Prize. So these are half gods. They live up there somewhere. And
there's a debate whether or not the professor is above or below the god. These guys clearly above.
Very above, yeah. Because, I mean, Aki and I, we are still waiting in the mail every day for where is that one letter, that one nomination, and it's still
every
not
day
there.
going to the mailbox.
Yeah, every day. No,
Nothing.
nothing. Anyway, so they, Klein and Sommerfeld, together with Fritz Noether, they were in Gyroscope, and they wrote a 4-volume set about this wide on gyroscopes. And the last volume, number 4, was on applications of gyroscopes. And if you're in gyroscopes, you see gyroscopes everywhere, right? So they also saw a gyroscope in a bicycle. They said, oh yeah, the gyroscope in a bike, and that stabilizer thing must be... Well, they knew their classics, so they knew the work by Whipple and Carvalho. They went through their model, and then they started derivating the equations of motion again, and then showing that if you kill the kill the gyroscopic effect, It can never be self-stable. Very clear. And the argument was cool. However, if you went through the math, they made two small sign errors in that derivation. Two minuses which should be pluses here. If you then check if you kill the gyroscopic effect, it's not so obvious anymore that it's always unstable.
Can I make a comment here? So these mistakes, these typing mistakes, were detected by your team.
Yes. Not by me, I'm not so sure.
Yeah, but your team. And who could think that, there is this guy nominated to get the Nobel Prize this many times, and they publish an entire series of books. So not the single book, but the 4 books about the gyrus. So they don't know their business. It's your role too to be skeptical. It's very important.
Absolutely. And
it doesn't matter how big is a guy. People just make the mistakes.
Maybe that's the main lesson of this whole lecture. So there are 2 sign errors here, and they're not typos. They're really sign errors. They just made an error in the derivation.
Yes, it can happen. It can happen.
It can happen.
Humans.
It's
For
human,
humans.
of course.
So back to these guys, are they above or below the guy? See that they still below.
Anyway, there's 2 sign errors.
But anyway, so
imagine it. No, so please.
yeah, just another comment. Later in this class, I'm going to tell you another similar kind of example. And there was a really brave guy, young guy, that was going against the big professor, saying that, hey, you made a mistake. And that is, considering all the hierarchy in the universe and everything, is not easy, but it's your position to do it.
Yes. Yeah. Absolutely. Because what happened in this bicycle dynamics world, from the days of 1910, when you talked about bicycles and stability, people who thought, well, I know my stuff, always said, well, actually, Klein and Sommerfeld, they show that it's stable because of the gyroscopic effect. That's clear. I mean, there's no discussion about that, right? Well, there is. And even from those guys, you have to check that work. Anyway, we showed then that it's not so obvious, so it's not a gyroscopic effect by itself. I mean, it is beneficial and it can help. Yes, the signs are right. If you take a spinning wheel like this and it rolls over the torque in the direction, it's all correct and so on. But it's a tiny contribution also. That's what we noticed, and it helps. It's tiny, but it's not a necessary condition. So what is then? Well, of course, we also have the other team. Still one team left, right? And what do the other teams say? Well, it is the steering geometry. It's a strange geometry that you have like a caster wheel here. If the bike leans, it steers. And then that's a theory from 1970s, David Jones. He was a bit in doubt about the size of the gyroscopic effect. So what he did is he built a bike where he built a counter-rotating wheel next to the front wheel and a bit off the ground. And if you then have 2 rotating wheels in one frame, one rotating one direction, other one the other one, the net angular momentum in that frame is 0. So there is no angular momentum effect anymore. If they're both in one rigid frame then. So no gyroscopic effect for the front wheel. And he says, hey, mommy, I can even ride without hands. Very stable. Nothing going on. No problem. So gyroscopic effect debunked. That's not really necessary. But he said it's this steering geometry. So he built bikes where the trail is very large and the contact point is far behind the steering axis. Oh, very stable, I can ride without hands. He made one where the contact point is in front of the steering axis. Very nervous, I cannot ride without hands. He said that, so that is the trick. So this trail is the thing which determines stability. And then he went into the derivation, and the derivation is makes use of potential energy. And then he made a plot here, and on the plot he showed that if the trail becomes negative, then the thing is always unstable, and if the trail is positive, then the thing is stable. However, this is based on gravitational energy. The gravitational energy in a bicycle, in a moving bike, is the same as in a stationary bike. Speed has no effect on the gravitational energy, right? If we then correct his reasoning by including the dynamics effect, then it's not so obvious anymore that a negative trail is making the thing unstable. Or, in other words, that trail is the dominant factor which determines stability. So we debunked gyroscope, we debunked trail. Nothing left, right? The only thing left is the question, what makes a bike self-stable? Well, we as engineers then say, oh, that's super easy. We just go back to our equations. So here we have the model, right? 3 degrees of freedom. We just have to investigate how the stability, the eigenvalues from the characteristic equation, depend on the parameters. Now we already saw the dependency of forward speed, but now we want to know the dependency on the geometry of the bike or all these aspects. Now how many parameters do we have in a bike? We have about 27 parameters because it's a three-dimensional objects. We have, first of all, we have wheelbase, we have a head angle, we have a trail, we have 4 rigid objects, 2 wheels, a rear frame and a front frame. They all have mass and mass moment of inertia. If you add up all these quantities, you have 27 parameters. Of course, you can do some non-dimensionalizing. Then you have 25 parameters, still a lot. And then you have to write down these equations of motion in terms of the parameters, which makes it rather messy. Then you have to form the characteristic equation from that in terms of the parameters. And then the stability is the Routh-Hurwitz criteria, which means that you have calculate from these ones the coefficients. You have 6 equations which all have to be positive. And these 6 equations come from the leading factors of this 4th order equation for the characteristic values, eigenvalues, and they are in the 25 parameters. Now, what you would do is you would print the output, and then look through the output, stitch your way like this must be positive, and that must be positive. So let's print the output. Well, then with the print, we can paint all the walls in this university. And still, we need some more walls. It's undoable. The output of that is not, as a human, you cannot read that. And as a computer, you also, these are all inequalities, all must be larger than 0. Computers cannot solve that. So we're stuck.
Just that this happens every now and then when you use even when you use a symbolic math tool. You know, you say that, okay, do the math.
Yeah.
And then you click the enter. And nothing happens except your computer dies.
Yeah.
And then you try it again. So what went wrong? You died again. And it's never going to give you anything.
Yeah. First the ventilator starts.
Then you're coming back next day and still the same.
So what to do? Well, one way is, of course, to make the problem even simpler. So that's what we did. We say, okay, let's make a very simplistic bicycle, and we call it a 2-mass skate bike, but which still has the flavor of a bicycle. Well, we don't want gyroscopic effect, right? So we kill that. So we put it on skates, and in the Netherlands we can do that here too. Right? You can put it on skates, no problem. And then what else? Oh yeah, we make it such that there's no trail, that the steering axis really hits the ground at the contact point. And then for the rest, we make the mass very simple, just a point mass somewhere on the rear frame and somewhere on the front frame. Now we have a few parameters. So the non-zero ones left are 8 parameters. And with these 8 parameters, it's doable to write down the Routh-Hurwitz criteria, which is here on top. So this is the Routh-Hurwitz criteria. And then all these 6 should be larger than 0, should be positive. And by writing down these leading coefficients, I step back a little bit. So all these leading coefficients here, we can stitch from one equation to the other. If this must be positive, then that, and then that must be larger than that. And so this is all fits on one page. This is doable, right? And then we come to the following conclusion, that in order for that machine to be self-stable, the following condition is on the mass distribution. Because there's no gyro, there's no trail. What else is there? Well, it turns out that the mass of the front assembly should be in the shaded region. If the front assembly mass is in this shaded region, here unconditional, in this other region conditional, but that's not immaterial, it's not so important. If that's the case, then the thing can be self-stable. And here I plotted the eigenvalues. Again, you see it starts unstable, and then from a certain speed on, the thing is always stable. Without gyro, without trail. So apparently with a mass. Now, to know that it's not about small numbers, we make a real multi-body dynamics computer model, and we do large angles, etc. And we see, hey, yeah, the thing stays upright if we hit it sideways. So the next step is, of course, to do the experiment and build the machine. Now, building the machine is, of course, a bit difficult. We do have ice, but we don't want to go outside all the time. So we make it such that we have wheels, but we have a counter-rotating wheel on top of it in the same frame, so there's no gyroscopic effect. We make it with fiberglass reinforced stuff so that it's very light, and we have real point masses. We take good attention to construction details, like we want almost no friction and so in the bearings. We make sure that the trail is zero or even a little bit negative to be sure, because you have a finite contact region. And in the end, we have the machine. We go to the sports hall, we propel it forward, we release it, and the thing stays upright. No problem. And we do the same. We propel the thing, and we're going to hit it sideways. And if you hit it then sideways, it starts oscillating a little bit, and then it gets upright again. And so clearly, this is the living proof that a bicycle can be self-stable without gyro or without the trail.
This is what we publish in the Science.
And this is the topic of the paper in Science. And the title is, A Bicycle Can Be Self-Stable Without Gyro or Without Trail.
Now, remember we met 2001. And that was the time that you initiated your studies in bicycle dynamics.
Yes.
And right after that, 10 years.
10 years.
You
Yes.
make a paper in Science. So
Yeah.
it happens like no time.
Yeah. In
That
between,
gives a little bit of perspective what is needed.
what it
So you
takes.
can have a big dream, but it's not going to happen tomorrow.
No. And I needed a lab, of course, to do the experiments, and I needed students to do the work, because I can do nothing, right? And of course, this actually builds on another paper, and that's a paper with the Proceedings of the Royal Society, and it's a journal where Newton also published, and in that journal, in 2007, we published on these equations of motion of the bicycle, because when we looked in the literature, we found a lot of literature, but most of the papers got different results. So most of the papers had small errors, or even large errors in it, or total wrong assumptions. And we couldn't find, well, until 1956, that was the first who had the correct equations.
So when was it again?
1956. That was the first one. Well, he was not aware that he was correct, of course. Everybody thinks he was correct. But even Kleinmans, even Whipple and Carvalho thought they were correct, and they made also very small errors, something with a sign somewhere. Not so important, but still small errors. So 1956 was the first time. There was Döring in Germany. He was looking at motorcycle dynamics, but made a very simple model like this bicycle, 3-degree of freedom model. He was correct. It was also nice that this Döring, he did experiments with a real motorcycle. So in 1956, doing experiments, measuring angles, angular speeds, and it has to be done with all electromagnetic things, with writing on paper roll and not wax roll. It's a little bit after wax roll, but still not the fancy stuff we have nowadays. Very nice. What else can I say? Oh yeah, and why did we say we have the right equations? Well, we are not up nose. We got the right equations because we were a team. It was me at Delft working on it. It was my friend and colleague Andy Ruina at Cornell working on it. And it was Jaap Meijert, my friend and colleague from Delft, who was then working at Nottingham University on motorcycle dynamics. And in this triangle, we were working on that same problem. And in that triangle, we, independently of each other, were deriving the equations of motion and comparing. And that is a very important lesson also for you. Whatever you do, make sure that there's somebody else who, independently of you, without any bias from you, does the same thing. And then you can check. Now, I already heard that your theses are already checked here. There's one who looks at the units or something like that, and there's another guy who looks at.
Dissertations are very no. It's like a final policy work, making sure that there's no serious time.
Yeah. Okay. So that's the policy.
Work party. This is something that is very Finnish work. I don't know what it is actually in Finnish, but in Finnish it's called tau.
Okay.
Meaning that you get together and work together.
Okay.
And it's kind of a party.
Yeah, well, actually, so that is good at the end, so for the polishing part, but also during the research, you have to do that. Really have to do that. Always ask your colleague, hey, we found this, can you please take a look at it? And then instead of giving him your work, you say, hey, why don't we independently derive this and then compare? Okay, there are actually on YouTube, there are very nice videos, a lot nicer than how I can tell it. They tell in like 10 minutes this bicycle physics stuff. And of course they lean heavily on our work and so on, and that's perfect. But they have a nice way of telling it and showing it. And it's this was minute physics.
Another word of warning, because I too watch some of these physics in bicycles, and some of them are complete nonsense.
Complete nonsense, yeah. But
they make no, I mean, that is they're absolutely off.
Yeah, exactly. But
they speak about powers and others that they have no idea what they are.
Correct, yeah. But some are very good, Veritasium and the other. Okay. How are we doing on time? We need question hour, right?
Yeah, we need to discuss.
We need to discuss, yeah. I wanted to talk about control, but we need to discuss, I guess. That's far more interesting. Questions?
Comments?
Yeah, please.
So if you proved that it wasn't the trail or the gyroscopic effect, what was the reason why it was stabilized?
Thank you for the question. So let's go back to the machine. This may be a good picture. So if we look at the machine, and then what do we see? Well, it is first of all it's very strange how the mass is distributed. This one is high up from the rear frame, and from the front frame it's a bit lower, but it's in front of the steering axis, meaning that if the bike falls over, then it will start steering, because it's an unstable configuration, right? So it will automatically start steering in that direction of the fall. So apparently the mass, if the mass was behind here, that wouldn't happen. It would steer the other way. So apparently how the mass is distributed here makes it such that it steers into the fall. Now it still has to do it at the right time, the right amount, and that has to do with, then the mass can only be in this region. So in this case, it's the mass distribution which triggers that mechanism of steer into the fall.
But how it is in normal bicycles when the mass is between the tires and
I'm talking here about the mass of the front assembly. So in normal bicycles, my feeling is that the trail and the gyroscope are more dominant than the mass, than the contribution of the mass. Yeah.
In the second slide, you have given that for self-stable, the velocity must be greater than 3.5 and less than 7.9. The velocity is like this. You have 4.6
Yeah.
or something. So I'm asking, it doesn't depend on the mass.
Let's go to that slide.
Second or third slide.
Yeah. So, correct. So, what I plot here are these eigenvalues as a eigenvalues as a function of forward speed. And for this case, which is a very specific case because it's a standard bicycle of a wheel size this and with mass as that and the person of that, all these for these specific 25 parameters. And how do we choose those specific 25 parameters? Well, approximately a city bike with approximately an average person on it. So it's for what we call the benchmark problem. So we took we designed a bicycle which was this is about average with the daily bicycle. And then of course you can say, well, here you studied the effect of velocity for that standard bike on the stability or the eigenvalues. You could also say, well, let's change the wheelbase or the mass distribution. Be my guest, please, because this stuff is all online available, and you can change masses and you can change everything and every time calculate again what the stability is. Yeah. Yeah. More questions?
What is the speed where the stability doesn't anymore, where the bicycle can't correct itself anymore?
That's a good question. So if you look at the progression of these eigenvalues with speed, and if you have to guess, then you would say, how would this continue? Well, guessing is always dangerous in engineering, but let's try. So, well, you would say, well, it looks like it's going straight up. So, my guess is the frequency will just increase with speed, right? Now look at the stability. Well, it looks like it's getting more and more stable with speed increasing, right? This one was already gone. Becomes probably more and more stable. And then this one, well, will it stay around 0 or what will happen? So you will think, oh, the faster you get, the more stable it will be. Right? That's our idea. However, you can also get it directly from the equation. And on purpose, I pulled out here certain terms. So I wrote the linearized equation in terms of speed, but also in terms of gravity. And if you say, I go very fast, you can also say, well, gravity is neglectable almost, right? You can neglect that gravity term. So we can cross out this term, that's not there. And then you see, here we have v squared, here we have v times velocity, and here we have a double acceleration. If we then substitute this exponential motion, we get these eigenvalues there, and we get v squared, or the eigenvalue times v, and we get the eigenvalue squared. And then we can scale a little bit by dividing by v squared, and we have just 4 eigenvalues, period. And the dependency of the speed is just linear, as we saw in the figure. So yeah, even theoretically you can say the faster you go, the more stable it will get. More questions?
We might have another visiting lecture about another vehicle, which is trains and trams.
Yeah.
Those are it's a big miracle that you can ride a train. So
That is true.
It's a big miracle that you can ride a bike too, but the trains are very, very unusual. So it's just surprising how they work.
Yeah.
Very surprising.
Maybe I can share one more thing. Now you heard all this nice science and the publication in science, and all very nice and very academic. But what is the relevance to society? I mean, why are you telling me this story? You're pretty apparently smart or able to. But what can we do with that? Does it make you happy or can it make the world happy? Well, my luck was actually that there is a large relevance to society because people are dying. And where are they dying? They're dying on their bicycle. They're dying in traffic. And in the Netherlands, the number of deaths and seriously injured in traffic go down for cars or all modes of transport except the bicycle. In the Netherlands, the number of deaths and seriously injured in cycling go up and remain to go up. Every year they go up. Now there is of course a major reason is that we are all getting older in general, and meaning we cycle longer, and if we get older we cycle longer, but we get also worse in doing the controls, etc. So there is a clear reason why there are more deaths, because it's exposure, more people are exposed, and it's more elderly. And that's also what we see in the figures. It's a lot of elderly. And it's a lot of single vehicle accidents. They do not get run over by a bus or a truck or a car, they just fall over. And that is the relevance. Since we now know about bicycle dynamics and control, we can help those people. We can make bicycles which help them stabilize by putting, like lane assist in a car, steer assist, where you make a mechatronic system that the bike falls over. If it falls to the left, you steer to the left. It does it by itself, and it helps you. And
this is very relevant because Adam is visiting us because he's helping he's participating in the class which is like how to make a successful proposal to academic effect. And it's in academia, in universities, people are usually telling their story in a way that, there is this gyroscopic force and, partial differentiation of this and that. And when you ask, okay, what's the important, what's the big benefit of your work? They say, well, my gyroscopic force is that that's a big benefit. It's not. This is a big benefit. And it's so hard to convince the people to look at that. They feel the research in this way that makes a big difference in society because they always do. Most of the cases they do. Let's put it this way.
And also in my case, so in 2011, I had the bike lab in Delft. My boss was saying, okay, where are your grants now? I mean, you now have a published in science. So I applied for grants. We publish in science, we know about the dynamics, we want to investigate further. Declined, nothing. Nothing happened. And I was, of course, totally demotivated. Like, hey, we are excellent. Well, why don't you give us the money? Well, they don't give us the money because there was no relevance to society. What can you do with it?
It doesn't really matter how much you're convinced that, okay, there is such a beautiful technology tool, they could care less.
Yeah.
So often you see that in universities there is a lot of ways to solve a problem, but it's unclear what is a problem.
Exactly. Okay, any more questions on that? I think we should finish up with
Yeah, this is
the
gonna be
time.
it. So we will continue next week then. Next week we go back to the more exciting things about error parameters and stuff like that. You're looking forward because I know that this is too practical for you guys.
Yeah.
But hold on, next week is going to be again Big Penny.
Cool. Okay. Thank you.
Very good. Hey, thank you, Adam. Okay, so next week, same time, same place.
Shall I stop the streaming
Yes,
also?
I'm going to go on direct. Because you can close it there, but let me first close it here.
Well, that's what I want.
No, you can close it
Yeah,
there.